Good morning, everyone. First of all, I'd like to thank the organizers for inviting me to give a talk at this international conference on integrated natural resources and environment management. My name is Diana Aga, and I would like to share with you some of the results from our research here at the University at Buffalo. The title of my talk is Contaminants of Emerging Concerns in the Environment and how they are occurring there and their effects in the treatment. So my research group is involved in studying the environmental chemistry of many different kinds of pollutants. One group is called the persistent organic pollutants, and this includes chlorinated pesticides, brominated flame retardants, and fluorinated alkyl substances. The second group of contaminants are the emerging contaminants that I will focus on today. And this will include chemicals that are used by us, like antibiotics and pharmaceuticals, and some chemicals that are considered endocrine disruption. And again, I will show you here that fluoroalkylated alkyl substances are also part of emerging contaminants. So what are emerging contaminants? These are chemicals that have only been reported in the last 25 years. And even at very low levels, like subparts per billion level, you could see adverse ecological and health impacts. These chemicals include both man-made and naturally occurring chemicals, and they are unregulated. In contrast to the persistent organic pollutants like DDT that has been the subject of research in the 1960s, the emerging contaminants are chemicals that have been dubbed as chemicals that are endocrine disruptors, and has been actually a subject in this book called Stolen Future, because they basically affect not only the mothers, but also the children. And they also include antibiotics that are used in agriculture and that are basically ending up in surface water and affecting fish. More recently, there is a set of chemicals called perfluoroalkyl substances, or PFAS. It's also called forever chemicals. That has been a subject of a recent movie called Dark Waters. So if you haven't seen this movie, I encourage you to see it. It's a very good movie, and it's based on a true story. So as environmental chemists, we use many different tools, and having the right instrumentation is really important. So for chemicals that are volatile, you need gas chromatography for separation, and for those that are water soluble and are not volatile, you need liquid chromatography for separation. And for detection, you also need to make sure that you have the right detection system. For example, in the next slide, I will show you that absorbance measurements is not necessarily the best for detecting chemicals that are in the environment. Instead, mass spectrometers are what we need to detect low levels. And not all mass spectrometers are created equal. There are low mass spec, low resolution mass spec, there are high resolution mass spec, and so on. So here's an example of the detection based on absorbance and based on mass spec. So in this chromatogram here, the detector used was a UV detector, and you cannot find any of the chemicals that you are looking at. Here we are targeting the analysis of tetracyclines and oxytetracycline and chlortetracycline, which are antibiotics used in animals. And when you use UV detection, you will not see any of this. You'll just see this background. But then when you use mass spec, you can see these individual compounds showing that the manure is contaminated. Now, it's really important to look at not only the parent compound, but also the transformation products. So when these chemicals are taken by the animals or by humans, they are transformed into different forms by epimerization, for example, which is basically rotating the carbon nitrogen here, or dehydration, which is the removal of water. So by these slight transformations, you might not detect the chemical that you're looking for if you're only targeting tetracycline, but the metabolites are just as important, because if you look at them, they're actually very chemically similar to the parent compound, so they are still biologically active. So it's important to recognize, and this is what I wanted to share with you today, is that pharmaceuticals that we take and personal care products that are present in our shampoo and our toothpaste, such as triclosan and lotions and all, are introduced into the environment through wastewater treatment plants, because many of the sewage treatment plants do not remove any of these chemicals to 100%. And it actually requires advanced treatment processes, such as the use of UV with hydrogen peroxide to treat these chemicals, to break them down. And not many wastewater treatment plants implement this advanced oxidation process. In this graph, I will show you that the carbamazepine, which is an anti-epileptic drug that is not removed during wastewater treatment plant, can be biodegraded only if you can first subject the wastewater through advanced oxidation process with UV and hydrogen peroxide, because the carbamazepine is converted to these degradation products that are easily metabolized by microorganisms. So these chemicals here are produced during advanced oxidation and corresponds to this peak here in the radiochromatogram. And as you can see, during biodegradation, they decrease over time. So this is day 0, day 30, and day 90. And you can see that they actually decrease over time. Other advanced oxidation processes include activated carbon or ozonation, which also provide high removal efficiencies in wastewater treatment plant. For example, in our recent work, we have shown that more than 95% of chemicals are removed when you pass it through activated carbon and ozonation. Okay. The other thing that I wanted to share is that veterinary antibiotics are also spread through manure application. So in the US alone, we use a lot of tetracyclines, more than 5.8 million kilograms in livestock production. And there are also other medically important antibiotics such as sulfonamides and beta-lactams that are also used. Well, the problem is many of these chemicals are excreted by animals intact, and this manure, as you can see here, are spread in lands, in agricultural lands, and are used as fertilizer, which means you are spreading antimicrobial residues in the fields. So we have shown in our research that the veterinary antibiotics from dairy manure are actually not removed even during advanced anaerobic digestion, and that many of these antimicrobials are taken up by plants. And in the US, some of these manure are stored for long term in lagoons until they are ready to be applied during crop season. And we have seen also that during the storage, the antimicrobial residues and antimicrobial resistance genes are not removed. So this causes a global problem of antimicrobial resistance, which is one of the most critical challenge of the 21st century. I know this is a little bit old data, but before COVID, it was predicted that in 2050, more than 10 million deaths worldwide will be caused by infection from antibiotic-resistant pathogens. And this is more than cancer and diabetes combined. It was also predicted that many of these infections will occur in Asia and Africa. So it's really important to take this into consideration. In this regard, we have research that actually investigate the occurrence of antimicrobials and antimicrobial resistance genes in wastewater treatment plant effluents all over the world. We have sampling sites not only in North America and Europe, but also in Asia, so including the Philippines. In this project, we collect water samples before and after wastewater treatment plants to look at antibiotic-resistant bacteria as well as chemicals. In this example here with a picture, I'm showing my student, Dina and Randolph, who went to the University of the Philippines and trained some of the local students to collect samples from wastewater treatment plants, from the environment, and also from the lakes to determine residues of antibiotics. We trained some local students to prepare the samples using solid phase extraction, where the cartridges are shipped to the US for chemical analysis. Here's an example of how sampling had been performed at Manila for looking at concentrations in receiving waters. We have students that go to India to do the same and also collect waters and analyze and prepare samples there. In Hong Kong, this in Dhaka, Bangladesh, so you could see many of the waters are just as polluted. And here's a contrast with people sampling in Switzerland, where you can see the streams are relatively cleaner. And so the way we do it is we collect about 500 ml water samples, acidify it and extract it using solid phase extraction. And then we ship the cartridge to the US at my lab here at the University of Buffalo. And we perform the liquid chromatography mass spectrometry analysis, or LC-MS analysis. In this analysis, we target many different chemicals from different types or classes of antibiotics. We have the sulfonamides and all these different chemicals, macrolides, tetracycline, and quinolines. And we also look at chemicals that are not antibiotics, including antidepressants and other pharmaceuticals and personal care products like acetaminophen and other chemicals. So it is important to measure not just antibiotics, but also other chemicals, because they have been shown to also induce antibiotic resistance in some bacteria. So for example, triclosan and the antidepressant fluoxetine can induce multiple antibiotic resistance in E. coli. So here's some of the results that I'd like to share with you. In this example, I will show you the comparison between the surface water in Sweden and Switzerland. And here for Sweden, the highest concentrations were around 500 nanograms per liter in the influent. So this is what's coming into the wastewater treatment plants. And you can see at the effluent, which is what is after what comes out after treatment, you still have a lot of macrolides being discharged. In the upstream, there is nothing because, and in the downstreams, you see some, and it's a little bit less because it's now diluted. The fact that there is nothing on the upstream means that the chemicals or the antimicrobials are only coming from the effluent discharges. And it's the same thing for Zurich, Switzerland, where you have a high amount in the influent, so what's coming in, but they are mostly removed during treatment or after treatment. In contrast for India, so we look at two different kinds of wastewater treatment plants. One has lower, but this one has a very high concentration, almost in a 50,000 total concentrations of antibiotics. And you can see that there are concentrations remaining after treatment, and that the upstream is even higher in concentrations, which means there is a source of these chemicals that's from an untreated sewage. And then the downstream has also leftover quinolines, which means they have not been removed. In Hong Kong, it's the same. We have very high concentrations in the influent, but most of them are removed, but still at higher concentration. Now, Manila, and we sampled two treatment systems. One has more in the influent, about 2,000 here, and you can see that the effluent in both cases have high concentrations of antibiotics, which means that the conventional treatment systems were not that effective in removing many of these chemicals. In contrast, you will see that in one of the treatment system in US, the chemicals already downstream have lower concentrations, although you will also see that even in the US, sulfonamides are also not removed 100%. In Dhaka, there's even more concerning because you will see that in the river, you have high amounts of chemicals, especially ciprofloxacin, which are third generation antibiotics. So that's a little bit concerning because that ciprofloxacin are one of those antibiotics that are given to infected patients when none of the antibiotics work anymore. So the fact that they're also existing in the environment is concerning because we don't want resistance to develop in bacteria against ciprofloxacin. More importantly, here is the data showing antibiotic resistance genes. And these are not the chemicals, but these are the genes that can be transferred from one bacteria to another through horizontal gene transfer. And again, this is even more concerning because when a non-pathogenic bacteria has an antibiotic resistance genes, this can potentially pass these genes to a pathogenic bacteria that could infect a person, and that infected person may not have any antibiotics to cure the disease, and that's a little bit scary. Now I'd like to switch the last few minutes of my talk to these chemicals called PFAS, or per and fluoroalkyl substances, because one of my students actually did some sampling in the Philippines and Thailand, including bottled water. So she collected samples from Laguna Lake. That's Grace, who graduated from UPLB chemistry. She looked at the concentrations of PFAS, which are also called forever chemicals, because the fluorine-chlorine bond are very strong. And these are some of the examples of PFAS, the 8-carbon chain carboxylated compound and the 8-carbon chain sulfonated compounds, and then the telomers. The PFAS are abundant in the environment and expose us humans because they are present in many consumer products, such as pizza boxes and microwavable popcorn and cookingware and so on. So on a daily basis, we are pretty much exposed to many of these chemicals that accumulate in our blood. And this can be passed on from human breast milk to infants. In this work, we collected samples from both the Philippine lake and lakes from Thailand, including water sources that are being used for drinking water. And then we also collected bottled water samples that are commercially available and analyzed them for PFAS. So what's interesting is that the Laguna Lake, the sampling sites, have detectable levels of PFAS, and these are all the many different kinds of PFAS that we were analyzing. But the chemicals there, the PFAS in the Philippines, are relatively lower compared to the PFAS found in Thailand. So I guess that's a good thing. Here are some graphs that shows, here is the PFAS in the bottled drinking water, in the Philippines. And you can see, again, in some ways, it's good news because it's actually lower than what you see in China and even what you see from Brazil in the Philippines, in US, here, Brazil and US. So the bottled water in the Philippines in some ways is cleaner compared to Japan. I think that's South Korea, and this is Spain, which are very high. And in bottled water, this is the data for the Philippines, and compared to Canada and France and Spain, the bottled water are still lower. Okay, so I'd like to conclude this talk, so there's time for questions. That, you know, before I was told when I was back in the Philippines that dilution is the solution to pollution. And that is not true, because in the Great Lakes, where we are here, we have a big, large body of water, and we are still detecting pollution or contaminants. So we should say that education is the solution to pollution. Okay, with that, I'd like to conclude my talk, and would like to acknowledge some of the funding agencies and all the students that have worked on this research. So thank you, and I would like to end this recording, and hopefully there will be some questions. Thank you.